All right, everybody. Section 6.7, enthalpy in chemical reactions. Apply Hess's law to calculate the enthalpies of different reactions. This is one of my favorite types of problems, Hess's law problems. So we'll get right to it. Enthalpy in chemical reactions generally is going to be measured by calorimetry using our equation Q equals mc delta T. This can be reported in units of kilojoules per mole of reactant used or of product produced. Most often, given a chemical reaction, indicating the enthalpy change associated with the reaction of stoichiometric amounts of reactant used and product produced. So if we look at this reaction right here, this tells us that water can be formed via the reaction of gaseous hydrogen and oxygen. So we've got our gaseous hydrogen right here. We got 2 moles of that reacting with 1 mole of O2 to produce 2 moles of H2O. Question A, or I guess prompt A, is write the balanced equation that shows 1 mole of water produced. Uh-oh. Immediately, we hit a brick wall. Well, not really, because there's a very easy solution. This reaction that I'm putting a little star by that we've been told produces this much energy. Now, 1 mole of water is produced. In this reaction, we're producing 2 moles of water. I'll tell you this, it's very easy to produce 1 mole rather than 2 moles. You divide this by 2. You divide this by 2. You divide this by 2. And what do you know? You divide this by 2 as well. So your reaction would be H2 plus 1/2, and I know that I've told you all semester long, don't use fractions, use whole numbers, but this is one of those instances where you will use a fraction. One of the very rare instances. And then H2O, and your delta H equals, it's still negative, and it's, what would that be, 72 divided 236, negative 236 kilojoules. Okay, determine the enthalpy of the reaction units. Yep, done. I solved that before. Okay, another example of this, going in the opposite direction though. The equation in enthalpy for the combustion of methane, CH4, is as follows. CH4 reacts with 2 moles of O2 to produce CO2 and 2 H2O. That's going to produce negative 891 kilojoules. Determine the amount of heat produced by the combustion of 3.3 moles of methane. 3.3. Well, heck, you're just going to apply that to all of these. So this is going to be 3.3 moles of CH4, 6.6 of O2, 3.3 of CO2, and 6.6 of H2O. So the amount of heat produced, I got to get my phone out for my calculator here. Calculator. 891 times 3.3 equals negative 2940.3. Then it tells us for option B, determine the enthalpy for the equation where we basically double everything. I tell you this, it's not a very creative question. 891 times 2. Delta H equals negative 1782. Okay. So enthalpy change is equal to the heat transfer for a process carried out at constant pressure. Delta H is a state function. We've talked about state functions before. We don't care how something arrived at to be in a particular state. All we care about is the state that it's in. Where the value of delta H for a reaction is independent of the path taken from its initial to final state, delta H depends on what the reactants and products are and not on the particular chemical reactions that were carried out to get from one to the other. Examples of delta H for specific processes. You might see delta H of SOL, and that is, well, when a solid dissolves in a solvent. You might see delta H VAP for vaporization, delta H for FUS for fusion, and delta H for RXN, which is for a specific chemical reaction occurring in stoichiometric quantities. The enthalpy changes for some reactions are difficult to measure directly, and that is kind of the foundation for which Hess's law is kind of appreciated. These can be calculated by manipulating equations for other reactions with known delta H values. The way that I always kind of think about it is, well, I don't necessarily know how to get from San Marcos to Detroit, but I know how to get from San Marcos to Cincinnati, and I know how to get from Detroit to Cincinnati. Maybe I can sew those pieces of information together to get me from San Marcos to Detroit. When chemical equations are added together to yield a different chemical equation, the corresponding delta H values are added to get the delta H for the desired equation. This principle is known as Hess's law. Okay, so we need to be able to follow some rules for manipulating chemical equations. The first rule is that when an equation is reversed, the sign of its enthalpy changes. So here what we have is N2 reacting with O2 to produce 2NO. Our delta H is positive 180 kilojoules. Now we give that the Missy Misdemeanor Elliott treatment and you flip it and reverse it. Now we have 2NO that decomposes to N2 plus O2. What were the reactants are now the products. The delta H flips as well. It's negative 180 kilojoules. Okay, rule number 2. This is one that we've already kind of looked at with our earlier problems. When the coefficients in an equation are multiplied or divided by a factor, the enthalpy value is multiplied or divided the same. So here, from here to here, we're doubling it. So we're multiplying all of our coefficients by 2. We are also multiplying our enthalpy change by 2 as well. Manipulating chemical equations, rule number 3. When reactions are summed, the enthalpy of the overall reaction is the sum of the enthalpies of the component reactions. So we've got reaction 1, reaction 2. We combined all our reactants, and then we combined all our products, and then we said, okay, what's common on both sides? Well, O2 gas, what's common on the different sides? O2 gas is a reactant. It's also found as a product, so we get rid of it. CO2 in our combined reaction is a reactant and a product, so we get rid of that. Okay, so our final reaction is diamond going to graphite, just carbon going to carbon. Our delta H for this is going to be a combination of these two values. It's negative 395.4 plus 393.5. And ultimately, this should be a negative down here. That's going to be somewhere in the area of, what would that be, 1.9, negative 1.9 kilojoules. Okay, so we'll work through one practice problem with Hess's law. Here is our practice problem. Using the data below, calculate delta H for this reaction right here. Reaction number 1 shows carbon plus O2 yields CO2. It has delta H sub 1 of negative 393. Reaction 2, we've got CO plus 1/2 O2 yields CO2. Now what our aim is to manipulate these two equations, and maybe we'll only have to manipulate one of them, but manipulate these two equations such that we only are left with carbon, 1/2 O2, and carbon monoxide. Okay, so goal number 1, and the way that I always treat these questions is I want to find what are some common components. We've got solid carbon as a reactant. Now I want to look at reaction 1 and reaction 2 and say, where is solid carbon? Well, it's a reactant for or in reaction number 1. So I'm thinking, okay, if it's a reactant in my overall reaction, and it's a reactant in reaction number 1, that's where I want it to be. So I don't need to change anything there. Okay. So when I say I don't need to change anything, that means I don't need to flip reaction number 1. I want to keep that one in the place that it is. Okay, then I've got O2, one mole of O2. And if I look at my overall reaction, I have half a mole of O2. Okay, so that's a little bit different, but is that a problem? I don't think so. We'll revisit it later on. CO2. Well, CO2 is absent. Sorry, in reaction 1, CO2 is a product. And it's absent from my overall reaction. So my takeaway from that is I need to get CO2 as a reactant in reaction number 2. And so if I take reaction number 2 and I say reaction 1 I'm keeping as is, reaction 2, I'm going to flip that. I'm going to rewrite it. And whenever I rewrite it, I will say CO2 gas, include my subscripts or my states, that goes to carbon monoxide gas plus 1/2 O2 gas. Delta H sub 2 is not negative 283. Since I flipped the reaction, it's positive 283. Now what I like to do is I like to go ahead and cross out this reaction. I'm done with it. And I like to do that just because I want to keep my workspace a little bit ordered. Okay, so now what I'm going to do is I'm going to take all my reactants from reaction 1 and reaction 2 and combine them. Carbon plus O2 gas plus CO2 gas yields, so this is carbon, O2, carbon dioxide, 3 reactants. Okay, now my products, CO2 from reaction 1 plus CO, carbon monoxide gas, plus 1/2 O2 gas. Okay, so I've accounted for all of my reactants and all of my products. And I'm going to go ahead and erase all these little checks that I put over my overall reaction. And now what I want to do is try to cross out as many things from my reactants and products to get this overall reaction. So carbon, solid, is only on the reactant side. So I'm going to leave that. O2, 1 mole of O2 is on the reactant side, and 1/2 mole of O2 is on the product side. So what I do with that is I cross out 1/2 mole of O2, and as a result, I change this coefficient to 1/2. Okay, now that one's good. Now CO2, is that present as a reactant in my overall reaction up here? No, it's not. But CO2 is also present as a product in this combined reaction, so that will effectively cancel out. So now, if I look at my reactants, carbon, 1/2 O2, and carbon monoxide. Sorry, my reactants and my products. I've done everything that I needed to get that. And so there's no extra reactants or products left over. My delta H for this overall reaction is negative 393 plus 283, which would give me negative 110 kilojoules. All right. There are going to be practice problems for this in your homework. This is not the only sort of problem like this. These kind of have a bit of a range. Some are more difficult than this or more challenging than this. And so keep those fundamentals in place where manipulate. And then my recommendation is whenever you manipulate an equation, strike it out. Just because inevitably you'll get confused, or I personally get confused when I have like 2 almost identical reactions. I hope this was helpful. We're almost done with chapter 6. So this is another way that you can this is a way that you can visualize what's transpiring from the reaction that we were just looking at. So basically what we've got are a pair of reactions. We've got carbon and O2 going to carbon dioxide, and that is a reaction that will release 393 kilojoules. We've also got carbon dioxide decomposing into carbon monoxide and O2 in 1/2 mole of O2. And that is a reaction that will consume 283 kilojoules of energy. And so when you combine these two reactions, these different energy planes or these different energy levels, you come up with the enthalpy change for the overall reaction, because we don't have both of these events taking place completely. Instead, we have this combination of the two happening in sync with one another. All right, that's all that I wanted to add. Thank you very much. Have a good one.